Hi everyone, today we're going to talk through our analysis and redesign of deli meat slicer. So as is obvious, our product description, our product is the deli meat slicer used to cut down meat into thinner slices. Next slide. Here's an exploded view showing that all of the parts have kind of surrounded the base. Next slide. Our customer groups would be the same as before. Our primary customer is the food industry, and our secondary customer is anyone who just wants a deli meat slicer at home. Next slide. Our fast diagram has changed to account for trying to avoid using any component or part names in the fast diagram. And as you can see, we still want to achieve all of the necessary functions. Next slide.
Since the interim report, there's been no additions made to the fishbone assemblies. Our sequences are still bottom up as sub-assembly shown here. As seen in this chart, when we compared the two sequences, the sub-assembly turned out to be the better of the two.
Here's our function component mapping matrix. Other than changing a few of the function names to match the fast, there have been no changes. Next slide.
Looking at our bill of materials and rough cost estimation, any changes to the assembly process or any pricings are seen in red. A new total cost per part after all changes is $77.92. Through DFA and DFM, which will be discussed later, we had a total of about 8.32% total cost reduction. Next slide. Looking at our quad chart, all of this will be mentioned later, but this is what we mainly looked at when looking at redesigns. Next slide.
Looking at the functional differentiation and component commonality tables, we have updated these tables to include every function and component used in our product. Next slide.
Here's our first redesign. On the left, you can see the original design, and on the right, you can see the added locking mechanism to prevent the sliding bracket from sliding when being moved. The common interface is the sliding bracket being modified to allow the rod being removable. Next slide.
Our second redesign from the interim report included combining the blade cover and guard into a single part. We have included callouts to better visualize these changes. Next slide.
Our assembly sequence from the interim report has been adjusted to make it easier to differentiate the primary and secondary customer groups. Additionally, we've added some callouts to show the delayed differentiation and the effect of combining the parts, as Matt mentioned. Next slide.
We then now it's time to complete the design for manual assembly analysis. Here you'll see the manual assembly time was 118 seconds, or just under 2 minutes, and the efficiency of this was 0.33. To try and reduce manual assembly time, we made changes to a platform part. The platform part that we selected was the backplate because the quad chart showed that it needed redesign. It had relatively high assembly times, and the theoretical minimum number of parts showed that it needed changes. The changes that were made were that we combined the backplate and the backplate holder by DFA 1. We changed the orientation of the mounting hole and post by DFA 4, and we created asymmetrical mounting post and mounting post hole by DFA 7 to allow easier assembly. Next, we made changes to the slide plate. Also, because the quad chart showed that it needed redesign, it had a relatively high assembly time, and the theoretical minimum number of parts showed that it needed redesign. The changes that were made were that we combined the slide plate and the slide plate holder by DFA 1. We added the locking mechanism to the slide handle by DFA 11 to allow easier insertion. And then we added notches to the base plate to help alignment for assembly by DFA 11. The manual assembly time was decreased by 16 seconds when these changes were made, and that lowered the time to 102 seconds from 118. And the efficiency was increased from 0.33 to 0.38 after these changes. There was no impact on product function for either of these parts, but the changes to the slide plate will increase the part manufacturing cost due to a much more complex design, as will be discussed later, and there was no increase for manufacturing costs for the backplate due to the elimination of the backplate holder.
To improve our design for automated assembly, we redesigned the base part subassembly as seen in the two exploded views. Next slide. Using the quad chart and the DFA discussed in lecture, we redesigned the height and sliding handle, the legs, and the thickness knob. We added snap fits to the thickness knob using DFA 3. We reduced the part variety between the height and sliding handle using DFA 5. And we added a thickness at the bottom of the legs to avoid tangling and nesting, which is called out in DFA 8. Next slide. As you can see in the total handling and insertion cost tables, we were able to reduce our total assembly cost from $18.09 to $11.91. However, this does come with some increased manufacturing costs, as you will see later in the slides.
All right, so looking at our process selection, the first part we decided to look at was the backplate. Next slide. Here are the critical dimensions highlighted in red. We decided that the height and the length of this part were critical in determining any tolerances. Next slide. Here are the parameters. Note that due to the height and the length from last slide and from the component mapping matrix of what this part does, we decided to give this a tolerance of plus minus 0.5 millimeters. Next slide. After taking all of our parameters and running them through the process selection, we found that 2 candidate processes were sheet metal working and machining, with our recommended process being sheet metal working. Next slide. The second part we decided to go through process selection with is the leg. All of the important dimensions are listed below, with the critical ones being in red. Next slide. Here are the parameters. Again, like the backplate, we looked at the function mapping matrix to find out what a good tolerance for these legs would be based off of the criteria that they need to fulfill. They need to be a bit more tight, so we're giving them a bit smaller tolerance of plus minus 0.2 millimeters. Next slide. Overall, through the selection table, our candidates for this part were machining, injection molding, and compression molding, with our recommended process being injection molding. Next slide.
So now looking at the design for manufacturing of this injection molded part, we have the analysis of the before redesign costs and the after redesign costs. One thing to note, that the after redesign actually has a higher total cost per part. While this is an increase from the redesign, this is due to the addition of the clip on the leg, which allows for a locating feature and a snap fit feature, which is much preferred for the assembly sequence. As you can see, isometric view and other views denoting the key features that Robert called out are shown on the right. Next slide. Looking at DfM Pro for this leg, we were able to bring our redesigned part into the DfM Pro and actually saw that there were a few recommendations for design changes that it would have us complete. This being the case, if we were to redesign our part further, we would take these into account and definitely adjust our design based on this. Next slide.
On this slide, we can see the cost estimation for the original and the redesigned backplate. As you can see, the total cost per part went slightly up after the redesign. This is because the backplate and the backplate holder are combined into one part. So even if the cost seems to increase from the original to the redesign, the actual cost will be less since we will be using one less part. Next slide. On the left, we can see our redesigned part on DfM Pro. There were no recommended changes after running our part through DfM Pro, so that is fine. And on the right, you can see the bulk prices given after uploading our part to hubs. Next slide.
We then made a plan for product service systems. We created maintenance plans to ensure quality parts with warranty replacement parts, meaning the deli slicer routine maintenance and blade sharpening. Also, we will create a custom forum for users to communicate with each other about their experiences with the slicer. And last, we will offer recycle rebates to limit the number of products that end up in landfills. This means we'll offer rebates to users that want to get rid of their old deli meat slicers if they send it back to us rather than throwing it away.
So looking at overall benefits to our redesign, there are overall less parts. We completely removed any need of fasteners. It is an overall easier product to assemble, and the overall price reduction is driven by fewer parts. Some self-critiques that we can make in our design. We would have liked it if our DFA and our DFM didn't increase our price parts, and our DfM Pro had some redesign recommendations for the legs that we would take into more consideration if we were able to do this again and had more time. Also, if we had more time and we were able to start this over, we would contemplate a complete redesign of the side plate holder, not using the current geometry because it was a bit weird looking at it through SolidWorks, and we would consider different materials and manufacturing processes for our highlighted parts. This concludes our final presentation video, and we are now open to discussion and questions. Thank you.